computer. It always gives me weird settings. Okay, let's see. So this week, you learned about reactions. Finally, right? Sort of. Maybe I don't know. Maybe it hasn't felt like that long, but I guess you've covered a good amount of stuff before reactions, right? There's some kind of like preliminary basics and stuff that comes before it. Yeah, and now you're actually starting to see them. This is the first reaction that you can do, and in some sense, it's maybe like the most important one that you'll learn, because it is the only reaction, at least as far as this course is concerned, and well, you know, most people taking this course are really just concerned as far as the course is concerned. It is the only reaction you can do on alkanes, okay? Things without double bonds, things without any special functional groups, it's the one thing you can do. That is to say, like, for the rest of this semester and next semester, if you see something that has nothing, like no double bonds, no special features, it's just carbons and hydrogens, all single bonds, you know exactly what you have to do, okay? That is, there's only one thing you can do, and it's to do free radical halogenation, okay? Yeah, so I guess that's sort of what you have had covered this week. The quiz, I guess, this quiz thing is also, I checked the syllabus and I think it's on Friday. So I'll also try to kind of talk about the things that you will see this week and kind of give like an introduction or an overview of what you should expect, what you should look for, and kind of like the things that you should expect when it comes to actually solving problems related to it. That might be like strange because you haven't gotten to learn it yet. It doesn't, from what I saw looking through the syllabus, it doesn't seem like you're expected to know about stereochemistry yet. But well, that's okay. I mean, we'll talk about it, and I'll give a kind of overview, and then if you are like, what the hell is this dude talking about for that amount of time, you will see what I'm talking about, and it might be helpful to like run back through and see kind of what some of the points are that I've mentioned, maybe like after the lectures. But I think I'll try to be as clear about it as possible and not like throw some crazy unexplained terms at you. Okay. All right. Well, how about we actually get started? Oh, I can't. My screen isn't even sharing. It's fine. I haven't been writing anything, but be sick. Here we go. Share. Oh yeah. Okay. Now we're really talking. Okay. Cool. So let's make this smaller. Okay. So let's see. This week we've covered chapter 4, which is, well, I don't know what the title of it is, but there's something that's clearly about, which is free radical halogenation.
Sorry, can I interject? This
Yes.
is Alex. So we only covered in Dr. Tong's like Tuesday night. We only did like the very beginning of chapter 4, which was like the basics of free radical mechanisms. And then mostly it was like cyclohexanes, axial and equatorial, just as a heads up.
Okay. Got it. Are you operating under a different like quiz schedule or like exam schedule?
We're just very behind.
Ah. Okay. Yeah, I see. I was actually really surprised because it seems like this sort of like unit, like chapters 3 and 4, has gone very quickly, right? Yeah. In this sort of, I mean the quiz covers chapters 4 and 5, and chapter 5 is this week, right? So, okay.
Yeah, I think
Uh,
so. For this week, he was going to finish up chapter 4, and I'm sorry for interjecting. I don't know if this
no, it's
is.
no worries. Yeah.
So I think this week he's going to finish up chapter 4, but basically we got up to. We didn't hit on transition states yet, but we
Okay.
did talk about initiation, propagation, and the stability of like primary, tertiary, like carbon radicals. So that's pretty much where we're sort of at. But
Okay.
mostly,
So
most of the topic was stability of cycloalkanes and then cyclohexane and those sorts of things.
okay. The fortunate thing is that what you described about free radical halogenation of what you've already seen, those are the most important things. Okay. So I guess to start like kind of listing through and writing down what we've got when it comes to free radical halogenation. So uh well, first things first, you should know the mechanism. Okay. Um this is like sort of backbone knowledge that you will be expected to have. It is the most like I say this about a lot of problems. Like there are a lot of very standard organic chemistry problems, but you like should expect a problem that says write out the mechanism for free radical halogenation. Um, it will pretty much always come up. There are some twists, some variations on it, but like more or less, it's always very consistent. Okay, so this mechanism is split up into 3 steps. Okay, the first one is initiation. Okay, important part being that you need ultraviolet light, which is commonly denoted by like an HV or an H nu, like this Greek letter nu. And then it's followed by propagation, which leads then finally to termination. Okay. And conceptually, the important parts here is that with initiation, you start with something that's not a radical. In particular, you start with something that's like held together. And then with light, it gets split to 2 radicals. So you go from 0 radicals to 2 radicals. Okay. With propagation, you take a radical plus, well, something else. And then that'll react on its own, right? So this one radical here is going to hop over to there and it's going to react, right? I'm using a single-headed arrow here because that means only 1 electron is moving. For pretty much any other reaction in this course, you'll use double-headed arrows, which means 2 electrons are moving. But with radicals, you only move 1 at a time. So, okay, now you get, well, I should say that this will take off a hydrogen, right? Let me put like an R there, okay? So it'll take off a hydrogen and that bond will split. So I should have put not a minus sign here, but instead I should have put a hydrogen. And you'll also get this extra stuff as a radical, right? And then, well, and then this stuff over here as a radical is going to react with something else that's not a radical, okay? So it's going to react with something else, okay? Most commonly, we say it reacts with one of these X2. In particular, it reacts with this X2 because we need to get another radical out. So we have to split something in order to get a radical. So, okay, it's going to take a single-headed arrow. From this bond over here, it's going to also do a single electron, and then a single electron is going to stay over there, right? So we wind up getting a halogen on our R group and then another halogen radical, okay? Conceptually, again, the important part here is we start with 1 radical and we go to 1 radical again, okay? It's propagating because we always wind up with another radical again, so we can continue the reaction, right? And then termination is when we go from 2 radicals to no radicals, okay? So 2 things that are radicals combined. And termination is kind of that step where they could say, okay, list 4 possible termination reactions or something. Like, there's a lot of them because all you have to do is take any 2 radicals that you got at any point and stick them together. Okay. So yeah, this can get kind of messy because we could do something like an R group, an R radical, and then an R radical. And why not? We could put 2 of them together like that. Okay. We can very well take what we want. Well, what we would like to happen would be something like this, right? Because then we just get more of the desired product. That would be kind of nice, right? Doesn't always happen. You wind up getting some mess with these reactions, and it's kind of unavoidable. These are like not the cleanest reactions, but they're very common. Well, so there are sort of ways of cleaning them up, but that's something for Orgolab. Yeah, so we have these sort of 3 steps of how this reaction goes. Okay, all it needs is light to start, and then it'll kind of keep going on its own. Okay, I tried to keep this very general because, well, this X2 can be a lot of things, right? I guess maybe I'll write over here. So this X2, well, okay, you know that it could be like chlorine, right? I've been talking about halogenation this whole time. Okay, it could be bromine. I think so. It can be iodine. Iodine is kind of like special or hard to react with because, well, it's not super reactive in this case. If I remember correctly, there are sometimes some special conditions that you need to get iodine to react into this. So not always, but the point is there are some other ones too, right? So I know one that comes to mind is something like this, like compound with silicon, and then if you put 3 methyls on there, then you can get some interesting stuff happening. But it looks like it'll be different, right? But it's kind of the same. Oh no, why did it take away my brush? Okay. Yeah, so it looks like you can get some more complicated stuff, but like it's just gonna split. It's just gonna split at this bond, like the same as what you're used to. If you're presented with a sort of weird thing like this, and it looks like it's your radical compound, like it's the compound that'll make radicals, like the simplest thing to do is just split it in like the middle where it is. Like don't panic. It's okay. It's just gonna be split in the middle. It's weird. I say this because like I remember when I was taking the course, like this was something that came up and it totally caught me off guard. And then I was like, okay, well, whatever. I'm just gonna treat it like the same thing that that we've used all along, and that's what you're supposed to do. So yeah, just do something like this if it comes up. And then with this R, I also kept it very general. And well, the reason that I did that is because this is kind of an interesting point, and it's one that's worth looking at now. So for this R group, the halogen, so it will react with, well, I guess I'll say the most stable position. Okay, so something like that. What do I entirely mean by that? So the idea is that this depends on the halogen, I should say, right? So chlorine will react wherever. And then bromine. So for the most part, we tend to just look at chlorine and bromine. Other things in this like course, you can generally treat as reacting pretty similar to bromine, or they'll give you like specific energies for the bonds, and they'll say, and then you'll be like kind of expected to predict whether whether it reacts selectively or not. So bromine reacts selectively. Okay. And this gets at something which is like quite important, which this is like definitely a term that you should know about and be familiar with. This gets at the Hammond postulate. Okay, which is this idea that the transition state resembles either the product or so either the reactant or the product, depending on whichever is closer in energy. Okay. So whichever one is closer in energy, well, it's going to stick with that one. So for bromine, what happens is that the product is actually, so if you're doing like a free radical halogenation, and you have here energy, and this is this reaction coordinate, which, well, we're not going to worry about what that means because it's too complicated for this. So if we have like, I guess just here, this radical X, it's up here. So for bromine, if we're going up here in this energy diagram and we're going to this R dot and this HX, okay, going up here, yeah, I guess this reaction has to be endothermic for this product to be closer in the first place. So, well, this holds up. The products are closer, okay? The products are much closer over here than they are down to here. Okay, I should have written bromine instead of X. Okay, so here there's that transition state. Maybe I'll use what might be more familiar for this course, which is just say TS. Yeah, so this transition state will be more like the product over here, meaning its stability will be determined by whatever is most stable on the product side. Okay, so this is all to say that that bromine brominates selectively. Okay, so bromine as selectively. So what does that actually mean? Well, let me scroll out for a moment. Okay, so what that actually tells us, well, we have to look at the stability of the radicals, and in general, having more electron density where that radical is going is going to be better. It's going to be more favorable, right? So, well, then we wind up getting that tertiary carbons are better than secondary or better than primary. Okay, so something like this is better than something that looks like this, is yet better than something that looks like this. Okay, because these carbon like these carbon R groups, they're bigger than the hydrogens, right? This is like a really hand wavy way to think about this, but like there's no way that I like can remember all of the details of this, and like the really specific like physical chemistry behind all of it. The easiest way that I like to think about it is just that the hydrogens are really small, so there's a lot of room for the electrons to go in that direction. But if you put a carbon up next to that carbon, that other carbon is like a wall. Like those electrons like can't really go further that way because there's just another carbon there, right? So that kind of keeps all the electron density in where that radical is, and that helps stabilize it. Okay, that is like not really the official reason, but well, for the sake of simplicity, I mean that's kind of the idea, right? Okay, well I've talked about just filling in that space where that radical is, but well there's kind of another way of doing this, which is that you can have a benzylic carbon or an allylic carbon, okay, because these have resonance. So well, if you have a carbon that looks like this, it can be whatever else, but as long as it's next to that phenyl ring, right? It's in the benzylic position. Or let's say you have like an allylic radical, right? That double bond, just the resonance from either of those is really stabilizing. It's very helpful. Okay. I guess while I'm at it, and I've already mentioned the Hammond principle, which is kind of one of these like specific terms that you should very much know. I might as well mention another thing that came up during lecture, which sort of, I'll just say it in passing. So you should be familiar also with this principle. Oh my God. So used to writing R groups from all all these reactions up here. So the principle of microscopic reversibility. Okay. And this is like, I kind of mentioned this in passing. It's not entirely related to free radical halogenation. In fact, it's really not related. But it will come up again down the line. And I know for me, like, just to give a quick story about it, or not really a story, but more just like justification for why I'm bringing it up. So it's mentioned like really early on in the course, like, what is it, week 4 or something of the course, right? Week 3, 4, probably 4, right? Yeah, so it's mentioned like super early on, and then it like never comes up again really, and you're like, okay, whatever. And then it showed up as the first question on my final, and absolutely nobody knew what this was about, like no clue, right? And it was just, the question was just define the principle of microscopic reversibility, and we had no idea. Nobody, like, I don't know anyone who got it. So that is to say, this principle is just saying if you have a reversible reaction, it goes backwards the same way as it goes forward, or rather, it goes forward as the same way as it goes backwards. Either way. So this is to say, reversible reactions go forward as they do backwards. So this is not relevant for free radical, but it's certainly a good thing to know, and it kind of came up in this discussion about chemical reactions and thermodynamics and kinetics. So for free radicals, but it's good to know. Okay.
I have a quick question about the Hammond's postulate. So you said that it's bromine selective because the transition state is closer to like the two products with the different degrees of substitution. So the reason chlorine is less selective is because it's closer, the transition state is closer to the reactants.
Yeah. So for chlorine, yeah. So what happens is that when you do chlorine, right? So this is the same diagram as before, except crooked, but that's okay. So when you're doing with chlorine, what happens is that this chlorine radical itself is very reactive, and it's like, well, yeah, it's very reactive, right? It wants to kind of latch onto whatever it wants to. And then over here, you just have this like carbon bond. with carbon hydrogen bond, which is just like your standard bond. Like there's not that much that's special about it. And what happens is that over here in this product, you wind up getting this chlorine carbon bond, which is really favorable. Chlorine really likes to latch onto carbon. And then you wind up getting, oh wait, oops. Maybe I'm saying this wrong. Yeah, okay. You get this carbon radical, and you wind up getting this HCl. And yeah, I think I was saying it backwards. So this HCl bond is really like strong. HCl is like a really favorable bond to have. So it goes down. It goes down in energy. Like the chlorine is so reactive that it'll kind of react like spontaneously, and meaning that it's a really favorable reaction, meaning that it goes down in energy, right?
Okay.
Yeah, so then, I mean, regardless of how we draw this curve, right, this could be all the way up here, it doesn't matter, right? The energy of the reactants is going to be higher, right? So it's going to be closer to there.
Yeah, but I was a little bit confused about like the fact that like a more substituted product will still be favorable for chlorine, like of course, but like it's less selective because like the transition state is further away. I'm kind of like confused about that concept.
Oh, okay.
Yeah.
Yeah. So this like, okay. Yeah, I see what you're saying. So I guess the idea is, well, what you're reacting has to like pass through the transition state. So in the case of like, for example, bromine, since the transition state is closer to what happens at the end, you're only going to get transition states that look like the most favorable possible case. In the case of chlorine, it doesn't really care what the final what the product looks like, right? It doesn't care what carbon it attacks onto, because the transition state is more determined by what you start with.
Oh, okay. That makes sense.
Right. Yeah. And the sort of idea is like, in this case, once it's up here, right? It's gonna go like it's gonna go wherever it's already set up to go. Whereas over here, like this, you only get this transition state that corresponds to what is most stable as a product. Yeah.
Okay. Yeah. Cool. Thank you.
Yeah. Feel free to interrupt always, guys, or send messages in the chat. Oh, I should be looking at the chat. Sorry, I didn't have it up on this other screen here. Let's see. In the textbook, there was an example where they showed X wall or wall as possible products for the termination. Oh, so they said like, yeah, okay, I know what you mean. In the textbook, they'll occasionally say like, you can get like your radical bonding to the wall, or R, when it was a radical bonding to the wall. They mean that like your radicals can react to whatever vessel you're using, like whatever actual container you're using to do this reaction. Yeah, I mean, you could write this, and I don't think anybody will mark you wrong, because like, I guess, yes, it's true, it happens. The idea is just like, once you have a radicals are super reactive. Like they'll go crazy. Right. So you have to do your reaction inside of something, and well, there's a wall to the reaction vessel, and yeah, you have radicals that are probably strong enough to react with it, right? Radicals are sort of one of those things that can react with any atom. There's a lot of atoms that like are super unreactive or something. But when it comes to radicals, it's just like actually ripping an electron off. So it, it can happen like that. That's like a possibility. In general, we sort of just like don't really, we don't really mention those cases because, well, they're not that interesting, I guess. And I don't know. I mean, it's not going to come off the wall, right? Like it's kind of already on the wall. It's going to probably stay there. I guess that's like a fine point. It doesn't really come up again. Every once in a while, the textbook does one of these sorts of things that's like, oh, did you know it can react with, this thing? And you're like, okay, whatever. It's strangely specific. Yeah. In general, I would just stick with, if you're writing out termination steps, it's probably more like interesting and informative and I guess like relevant to say it's going to react with like the other radicals that are there, right? So you want to take two radicals and stick them together.
I had like a follow-up question with major and minor products. So I know for bromination that because it's more selective, you would specify major versus minor products, but I wasn't sure if that only applies if you have a substance that has like primary and tertiary and secondary sites. Like, I guess what I'm trying to say is that like if there are multiple options where you can substitute the bromine, is that where you would have to specify major or minor? Because like the bromine would want to substitute at a most stable point, hence the major product.
Yeah. So you usually just have to specify when well, okay. Maybe let me give sort of two answers here. So if you're being asked to specify the major and minor products, then when it comes to one of these like bromination reactions, usually there will be like they try to give like a clear spot where it happens, right? So most commonly you'll get a compound that looks like this or something. And well, here in this case you have one tertiary place, a bunch of secondary, and one primary, right? And well, there's one major product and then a bunch of minor. Maybe there will be a case where they give you multiple places that are ideal or best to react with. If that's the case, you should, I guess, write more than one major product, like two or something. If there's like two tertiary sites, then okay, I guess you can write multiple major products and then maybe a bunch of minors. This is like sort of a thing that's, I guess, like relevant now, although again, this is like the only reaction you can do with things that are with alkanes, things that are just hydrogens, carbons, and single bonds. Eventually, and like by that I mean relatively soon, you could just write the major product eventually.
Okay.
Soon. Okay. It'll be just like, this is like such a common reaction to write that it'll be fine for you to just say like, yeah, I'm gonna react this. Okay, well, it's gonna give me this, right? Yeah. For now though, I would say, it'll probably be, I think whenever I've seen problems about this, they give like a place that's kind of clear where it's gonna brominate. If they give multiple places that it might be clear, you could also say that it would be a mixture. Like of major products.
Okay.
Yeah. Yeah. Okay.
Thank you.
Yeah. Let me this. Here we go. Okay, cool. So that's a whole bunch of stuff, and I've kind of talked about this for a while. Just, I guess, to kind of go through like some of the important stuff that you'll see this week, and kind of get into the part that will, like, I guess, matter and be relevant for the quiz. So the next like chapter or section is stereochemistry. Okay, and the sort of key idea here, this is like a really vocab heavy chapter. The sort of idea is that we have stereoisomers, okay, which these are, you've already seen isomers, like in the sense that they're different like compounds, right? You could have something that's an ether and an alcohol and it has the same formula, but they're certainly different structures. Stereoisomers have the same bonding patterns. So it has the same bonding, I guess, say bonding pattern. And it has, the atoms have different spatial position, though. Okay. And well, if you were here last week, you remember I kind of mentioned something along these lines, right? So there's this idea of a chiral center, right? And this is a carbon atom, typically a carbon atom. There are some exceptions. So a carbon with 4 substituents. All right, what does that actually look like? Well, if you have a carbon and it has, let's say, a hydrogen and, I don't know, let's give it a chlorine, and then we'll say coming out of the page, we have this methyl group, and then, okay, let's give it also an ethyl group, okay? And you'll notice that I drew in this wedge and dashed bonds, and that's actually important for this point, right? And what happens is that if we take a mirror and we look at this molecule through a mirror, here drawn by a dashed line, okay? So I'm gonna draw the exact same thing, except it's just reflected now. Okay. What you'll find is that these are not the same compound. Right? So they're not. And this is something that takes like a lot of time to wrap your head around. And it takes a lot of like really staring at it. You could try to think about this molecule. What could be really helpful, this is like one of those cases where these things are actually like useful, is if you have like one of those modeling kits, or even if you just decide to try to, like, I don't know, crumple up some paper and draw on it or something. There's no way that you can take this structure. There's no way that you could take this structure here in red and this one here in blue and put them on top of each other. Like you can't do it, because this methyl and ethyl have swapped positions. Okay, so we can take, for example, we can take this structure and we can rotate it by 180 degrees. Now we're not changing anything about the molecule, right? We're not flipping it, we're just twisting it in space. So you could do that, and what happens is, okay, you see carbon, so there's a chlorine. This is just drawing it so that it looks like the same setup as this other one, okay? And now this wedge and dash switch. So, okay, look, this methyl and ethyl over here have swapped places compared to this original. All right, it is not the same compound. These bonds can't just, trade places, okay? the fact that there are 4 different substituents causes this. If there were only 3 different substituents, this wouldn't be a problem, right? We would just be able to, in that case, you know, in that case, those two can for all intents and purposes, swap places. They're the same thing. So it's not an issue. But because we have 4 different ones, these two are not the same thing, right? Really driving that point home. Okay. This gets kind of messy. And to give you an example of that, the idea of having 4 different substituents is kind of a confusing one. So just to get this idea across, an example I saw in the textbook earlier, which I think is like really nasty, is if you draw this here, and then you put a chlorine there. Yeah, you arrange it like this, okay? And this looks so straightforward, right? Like, you know, you can flip it, right? You can flip it like this, like a pancake, right? Like this, and it's the same exact thing, right? It looks like there should be no problem. But okay, well let's you know, I don't know, I do the math here, or not do the math, but you know what I mean, right? And let's just look at this carbon. Okay, and what do we have? Well, we have this chlorine, we have this hydrogen, that's 2 different things. And then over here we have a carbon that has no chlorines on it. And over here we have a carbon with 1 chlorine on it. Okay, those are 4 different substituents. Yes, they're connected all the way back here, but well, that doesn't mean so much, right? It's just, if we're looking at that one particular carbon, are the 4 things that are attached to it the same? And no, they're not. Okay, so typically you will denote chiral centers like this with a star. And well, you could do the same thing on this other one. Okay, 1, 2, 3, and 4. Also a chiral center. All right. And what that means is, if I draw the mirror of this, let's see, the hydrogen is closest to the mirror, and this chlorine down here is closest, and then up here and down here. If you draw the mirror of this, these 2 are not the same compounds. Okay. Now this I don't know about you, but this is like a really weird way of seeing it. Actually, so I got a question about this 4th red one. Just to point this one out. So it's the same as with the one over on the left here. So we have this 1, the hydrogen is unique. The 2 of this chlorine. Over here, this 3rd one, we have carbons with nothing on it. And so this carbon doesn't have anything here. And then over here with we have a 4th one, which is a carbon that does have a chlorine on it. So over in this direction is number 4. Okay. That is like a weird thing to see. Yeah, maybe to draw like an example that isn't complicated by the ring, right? I mean, well, we could just draw this example, right? That doesn't deal with this whole ring thing, right? Now, because it's not on a ring, I need to actually be, you know, I need to be careful about drawing my wedges and dashes, right? Because we don't have a clear idea of what is up and what is down, right? Okay, if I draw something like this, right? Well, in this case, same as there, I have like 1, 2, 3, and 4. Okay.
Is there a specific way that you're counting, or are you just counting the substituents that are attached?
That is a very important question. I was about to get into that. So I've just been counting them, okay? So I've just been like labeling in terms of what numbers they are. What comes next is that there's a special way of numbering these things, which I haven't been doing, but I'll go back and correct that. So there's this system called Ingold Prelog. I think hopefully I spelled all of those right. And here's the way that it works. Okay. So let's say you have a carbon with 4 different substituents, right? That's the easiest way to identify if you have a chiral center. So let's say that you're there and you see something that has 4 different things, right? What do we do? Okay. Maybe I'll use the example that I kind of started with, because let's see, did I start with the methyl over here? Yes, I did. Okay. Here we go. Here's what we do. 1, look for highest atomic mass. Okay. Whatever's the heaviest, whichever atom connected to it is the heaviest, that comes first. Okay. Here we go. In this case, let me see what colors I used up there, just because I want to stay consistent. Up here, this was the blue molecule. Okay. Here we go. So blue, so, oh, whoops, I didn't actually add color. Okay, so first, chlorine is heaviest. That's 1. Okay, because here we're connected to carbons, here we're also connected to carbons. It's a hydrogen. Hydrogen is like always last. Okay, so look for whatever's heaviest. 2. If there are 2 atoms connected to it that are equally heavy, keep going. Okay. If 2 of them are equally heavy, then keep going. Okay. So this carbon we have is connected to CH. Okay. And it's also connected to C. Okay, here we go. Yeah, let me just keep using the blue. Okay, so we look in this direction and this direction. Both carbons. Okay, so we keep going. Here we have another carbon, and here we just have hydrogens. Okay. This carbon here wins. So the ethyl is 2, and the methyl is 3. Okay. And well, there's only one thing left. Only one left, which is hydrogen is number 4. Okay. All right. So what was the whole point of that? Well, now we get to actually play with this thing. And again, this is one of those situations where I know like last time I detested these things. I expressed how much I don't like these, but this is one situation where the modeling kit can be useful. Okay. So what you can do is you can build this molecule, like actually just build it in front of you. And what you want to do is take this highest priority, or sorry, take the lowest priority group always, so 4. It's usually hydrogen. Okay, very, very commonly it's hydrogen. So take the lowest priority and move it directly to the back. Right. So here we want to take this hydrogen up here, this number 4, and we want to put it behind the carbon. So what we're going to have to do is take this and move it back that way. All right. And that means this methyl over here is going to flip up to the top like that. Okay. This is one of those modeled situations, because if this is like the kind of step where it's really easiest to mess up. If you mess up in this step, it's going to flip which order, what your answer is, what your result is. Okay. So this is definitely a situation to be careful about it, right? It means this ethyl is going to move up front. This methyl is going to move up there. That's pretty complicated. Let me draw out exactly what that looks like. So we take, well, this structure that's up here, we move the hydrogen to the back. This chlorine, by the way, it's going to stay where it is, right? You could think about it as rotating around this chlorine bond, kind of like twisting it like that. Okay. Let me just draw this out. So there's a carbon, that chlorine stays. Up here, we got our methyl group. Down here, we have this ethyl group. And then way in the back, there's that hydrogen. Okay. And we keep our numbering from before. So chlorine was 1, ethyl 2. Here we go. 1, 2, and 3. All right. There's a lot of steps to this. This is a long, long process each time. Now what we do is these numbers are either going to go that way or they're going to go that way. Okay. The numbers either count clockwise or counterclockwise. Yeah. Clockwise or counterclockwise. There we go. Okay. So here's what we look at. If the numbers go clockwise like this, that's what we call R. Okay. R, it's for, I don't know what it stands for. Okay. If they go clockwise. So this here is R in between parentheses. That's just how they write it. And then if they go counterclockwise this way, then it's S. Okay. This is like the most, there's like a million things to remember here. So anything that you can think of helps. In my case, there's no way I'm going to remember clockwise R, counterclockwise S. Like that's just really specific. So better way to think about it is, in this case, you're going in this direction, right? And let's see. This is weird because like I'm facing the camera. So whatever I do is the opposite for you. And then I don't know if the camera is mirrored or flipped, which will affect things. But the way that I like to think about this is look at what direction it's going in. In this case, it's going this direction, okay? Think about it like driving. So if you turn this direction, you're gonna go right for R, okay? That one corresponds. So if you can remember that, okay, in this case, going clockwise like this turns the car right, then okay, that's R. And then, well, S is left. That one you just have to, it's one of those like mnemonics where it's like, oh, well, I'm gonna remember it because it's the opposite of the other thing. So yeah. But that's like, this is the easiest way that I've found to remember it, which is just that R means that the car goes right if you were turning it like a steering wheel. Okay, so that is what happens in this case. Why don't we go back through and kind of look at our other examples? So what we had earlier was, and by the way, the compound that we had mirror flipped, that when we took this thing and we flipped it in a mirror, that turned it into S. So if you flip something in a mirror, R goes from S and S goes to R. Okay. If we look at that other thing that we had earlier, just as an example, I think I had this chlorine up and this hydrogen down. Whoops, not like that. There we go. So I had it this way. Okay. Let's look. We're going to focus one at a time. We're not going to worry about the ring because that's just going to confuse us. All right. So here we go. Chlorine. And I'm going to say, okay, well, the rest probably doesn't matter that much. Here's how we count, okay? Heaviest is the chlorine. No question. Okay. Now we have to look either this way or this way. Well, they're both carbons. That sucks. All right. But over here, all that we get, I guess maybe I should draw the rest out. All that we get is another carbon. Okay, going this way. Over here, though, we get a chlorine. That's heavy. That's good. Okay. That beats any carbon any day. So we wind up getting that this side over here is 2, and this way is 3. And okay, well, that leaves only one thing left, which is hydrogen, and that's number 4. Could have guessed that one. Okay. You actually, it's very hard to get smaller than hydrogen. So yeah. All right. And now how do we do this? Well, we have to think about this ring like earlier, like a pancake, right? So now we have to flip it kind of upright so that we can actually make sense of this. Here we go. So we'll flip this to have this chlorine sticking out. Oh, writing really ugly chlorines. Okay. There's the ring, and there's that hydrogen going way back. Whoops. I write 4 because I'm so used to just associating hydrogen with the number 4 at this point. Yeah, and over here, this is where we had our chlorine and other stuff. All right. So here we go. Number 4 was in the back. Well, 1 is over here. Then we had 2 and then 3. Okay. There we go. We're going up this way. Okay. Yes, it's counterclockwise, but maybe more intuitively, we're turning the car left. Okay, that's S. Okay. The other carbon that's a chiral center, you could also do similarly. Okay, well, there we go. I've talked about this plenty. There's a few minor notes. There's something called Fisher projection in the textbook. I don't think you're gonna be expected to know that for now. You will be expected to know it maybe in the last few weeks of Orgo 2, but otherwise you probably won't be required to know Fisher projection. You should follow what your professor says, but it's usually not something that's covered. It's not super useful. Okay, and I guess there's one last kind of thing here, which I promise will do problems, I swear. So if you have multiple chiral centers, you can get this like a sort of broader class of stereoisomers, which is diastereomers. Okay, and I should mention that diastereomers also encompass cis and trans ring isomers, and it also captures E and Z cis bond, or E and Z double bonds. So the fortunate thing is that you already know how to do these. Well, you don't, but everything that we just talked about makes finding E and Z double bonds really easy. Okay. So you just look for, if you have a double bond, you can have a bunch of stuff over here, right? So I can call this, I don't know, I'm just going to call them a bunch of random stuff, A, B, C, and D, right? And let's say that, well, D is heavier than C. We're just going to go alphabetically here. So, and then B is heavier than A. Okay. So this is another example where there's like a silly and stupid way to remember this, but it's just way easier than thinking about it otherwise. And it stuck with me for 2 years, so it really works. So if higher priority, if it's on opposite sides, okay, then they're enemies. I think you see where I'm going with this, so it's E. Okay. Same thing with Z, you just remember it as the opposite, okay? If they're not enemies, then it's Z, because Z for, I can't even think of something that Z might stand for, so yeah. Okay. Yeah, there's one other thing to mention, which is meso compounds. So if a compound is like a diastereomer, meaning that, so if it has multiple chiral centers, but there's some way of drawing a mirror plane through it, it's called meso, which means it's not chiral. That meso compounds like haunt my nightmares because they like, no, you never expect them, and then every once in a while they'll come up. But I'll maybe get into what I mean by that. How about I actually, let's do some problems. Okay, and let's make a new page, and then I'm going to open up the worksheet. Here we go. Okay, because that was plenty of talking, and we should actually do a problem or two. Here we go. I'm going to take a screenshot of what we got here, this problem, and then copy and then paste. Yeah, okay. This problem is somewhat of a throwback at this point because, well, Newman projections are, well, they're kind of old news. So how about we just kind of run through it really quickly. Yeah, okay. So let's see, draw a higher energy Newman projection than what we have over here. Yeah. Anybody want to just tell me what a higher energy configuration would be, conformation would be? Well, we know it'll be eclipsed, right?
If you rotate enough so that the fluorines are gauche to each other and the amines are gauche as well.
Ah, let's see. So you're saying,
like if you rotate the back a few times.
Okay. Well, we could put, let's see. This fluorine, well, let's keep the front as is. Okay. And then maybe we could move this back fluorine to be over here. And we can move this NH2 to be over here. Okay, so we can do something like that. I'll actually say that there's a higher energy conformation than this, right? And part of that is because look over here, right? They're not really staggered, they're eclipsed, right? This is meant to be that these things are eclipsed, so they're bumping into each other, right?
Can we do that? Just shift it a tiny bit more so it's eclipsed.
In which direction? So
That way.
yeah, okay.
Yeah.
Yeah, so that would be it, right? The idea here being that, well, if we move all of these over just a little bit, right? The most important part here is that these NH2s will bump into each other. And these things are big, okay? Like they actually bump into each other. All those hydrogens really take up space, and that causes them to clash. So that would be it, right? And you might say, well, look, this means that these fluorines and hydrogens are like next to each other, right? And fluorine's big, but hydrogen's small, so that doesn't that's like fine, right? What really happens is the fact that these NH2s are that big and they're bumping into each other is like, that is the kind of most substantial thing that you can get. Just because those, like all those extra hydrogens are really going to clash into each other, right? So size dominates in this case, and well, I should say size dominates even more than having these two eclipsed interactions between the fluorines and NH2s, right? Because those fluorines are just single atoms. And in fact, fluorine's a really small atom too. Okay. So, well, I'm not going to draw it again. I'm just going to flip here. Okay. Lowest energy conformation, well, okay, we know that it's going to be staggered, right? Because we've been doing eclipsed, and everything is better than eclipsed. So, yeah. How about I draw what's in the front? Anybody see any good ways
Just
of...
make NH2 anti to the other NH2.
Yeah, okay. NH2, and we want to make sure that we keep things in the right order. So there's that fluorine, there's that hydrogen. Okay. Yep, that's it. Right. Yeah, we have these gauche interactions, right, which are kind of like, kind of ugly. But if we were to move what's in the back here at all, we would get gauche interaction between the NH2s, and those would really bump into each other. Again, that's sort of the theme here. So yeah, this is what we got. Cool. All right, that kind of covers that problem. We get this next one. Copy. Whoops. Okay, and okay, this is kind of like the standard. Well, I should say this is like a kind of one of those common things that you might be asked about, where you're just asked, you're given one of these sort of like reaction diagrams with intermediates, and you're asked to fill in. Okay. So okay, this is one whole overall reaction, and well, we're going from something at the start and something at the end. So I think it's no shock if I tell you that over here at the start it's the reactant, and over here at the end it's product. Okay, I did it again. Whoops, I can't get rid of that for some reason. Okay. And over here's the product. Okay, there we go. That's like 5 points or something, or however these quizzes are graded, number of 20% of points. Okay. Activation energies. So I'll say a common like place to get tripped up, and this is like never made clear, like nobody ever emphasizes this, and I don't know why, because it's a common mistake. For this reaction here, which, you know, the overall change in energy goes down, or the overall energy goes down, the activation energy is a lot more clear, right? It's just from where you start to where you end. Okay. There, that's the activation energy, right? That's it. But nobody, like people a lot of the time people will get confused for a reaction like this, which takes in energy, it goes up, right? Whether this is the activation energy or this is. So, so you should just always remember that the activation energy goes from where you start to the highest point. Okay. Always, that's what it will take, right? You have to go from the bottom where you're starting up to the top. It takes that much energy to activate the reaction. Okay, well, that kind of covers that. Transition states. Okay, somebody tell me how many transition states there are in this reaction.
2.
Yeah, 2. Okay. That's what I was going for. Okay. Over here, this is not a transition state. Okay. This is an intermediate. Not a transition state. Right? Do not call it a transition state. You will be objectively wrong. It is an intermediate. The distinction, if you really want to get into it, is the fact that this intermediate is at like an energy minimum, right? So things are gonna pool up there for like a moment, and so you can actually kind of like observe it. You could see it. It's really there, in some small quantity, but it's there, right? Whereas these transition states, I mean, they're the most short-lived things of all of this, right? Like they're at the top of energy. It's gonna do whatever it can to not be there for very long. So, well, it's gonna go either way. So it's just there in transition, right? It's not really stuck there. Okay, overall reaction, is it exo or endothermic? Anyone?
Exothermic.
Exo, yeah. So this is exothermic because it goes down in energy, right? Which is to say that energy has to go somewhere else, meaning it comes off as heat. Okay.
Adam, I have a quick question about delta H.
Okay.
In the lectures, he talks about when he talks about like labeling delta H, he says it's delta G, and like as in like gives free energy. And so I was wondering how he just neglects, like, are we considering them the same thing? Because they're like,
oh, yeah. So, well, this is like a question where you can really get into the details about it. I think for the sake of this class, it's just going to be considered the same thing. I also think specifically we're just going to be focusing on delta H in this class. Yeah, Gibbs free energy is, so it is a different thing. Like they aren't necessarily the same. But I guess, so delta H is like the enthalpy of the molecule itself, which is a more, it describes the molecule more than the reaction, right? So that's like a, I don't know, a kind of vague thing. So delta G kind of has to do with everything else that's going on around it too. So like it'll depend on like, I don't know, the solvent and like what conditions the reaction's happening under. Delta H is about like the bonds in the molecule themselves.
okay, so like we're neglecting like temperature and like entropy change, right? Like we're just saying that's 0. So then delta G just equals delta H. Like we're not considering like the reaction conditions at all. Or is that wrong?
So, well, yeah. So we're not really considering the reaction conditions here.
Okay.
If I remember correctly, and this is like, it's definitely more like thermodynamics than is really necessary, but it's worth asking anyway. So if I remember correctly, enthalpy is like the measure that already takes those things into account. like it already takes into account the entropy of the molecule. Well, I might be off on that.
Okay,
Yeah.
it's fine. I'll just assume that they're the same for the purpose of this
Yeah.
course. Okay.
Yeah,
Thank you.
you could definitely do that. There's like a subtle difference. Like, for example, when you talk about like biological chemistry, you use delta G to describe it because there's, you know, all these reactions are happening around in water. So there's a bunch of other stuff that you have to kind of worry about with that. With organic chemistry, we're not really focusing on like what else is happening around it. We're just kind of focusing on like, is this molecule itself as a molecule higher or lower in energy?
Okay, cool. No, that's fair.
Okay.
You can move on. Like, I don't want to take up all your time. I was just confused. Thank you.
Yeah. Okay. There we go. Okay. It says label delta H naught, so we can put the label here. And in this case, it's worth mentioning that this delta H naught is less than 0. Okay. It's kind of unclear because with the way I drew the arrow, it says it's going down, right? Or it says delta H naught is going down, so it's unclear whether that means delta H naught is positive or if it's negative because the arrow is going down. You could always play it safe by just writing delta H naught is less than 0. That works. Okay. And let's see, rate limiting step. Which of these two? First or second?
The first one?
Yeah. Okay.
Because it's higher in energy.
Yeah. There we go. So just, I mean, yeah, so you're right. Very subtle point. It's the rate limiting step because it has the higher activation energy specifically. You might have said that, and I just didn't hear it. But so 1 because higher activation energy. Okay. Activation energy determines how fast the thing will react, right? Because once it gets up there, it doesn't have to worry about anything else. It just slides its way down, right? But it has to get up to that activation energy. So that's what slows things down. Yeah. Okay. These are like, huh?
Oh, sorry. Because the rate determining step is endothermic, does that mean that like the radical that's formed is specifically the more stable one?
Let's see. So, okay, we haven't been talking about, well, this question is like kind of framed more generally than for free radical halogenation, but this is kind of important because, well, these reaction diagrams only come up in terms of free radical halogenation unless you get a really nasty question somewhere down the line. So, okay, if we look at it in terms of radicals, well, here we go. We have, let's see, what are we working with? H, some R, right? Then we're going up here, right? And then R, HX, and then it falls back down. Oops. And it falls down over to here, and then we got RX, and then X dot. Yeah, right? And then, so the first transition state is closer to
The product.
than to HR. Yeah, so this is like bromination, for example. So this is selective. Was someone about to say something else? I thought I heard someone for a moment. No. Maybe I won't scroll down. Yeah. Right.
So if it's closer to the products, it's selective, and if it's closer to the reactants, it's not selective? Or is that not the rule?
yes, only minor slight adjustment to what you said is it's closer to the intermediate in this case, right? Because I mean you would say this is the product, right? And this is the intermediate.
Can you
So this transition state is closer to the intermediate. That's all.
draw the arrow in of the activation state?
Yes. Wait, of the activation energy?
Yeah, sorry, yeah.
Yeah. So this is the activation energy right here. And then this is also the activation energy, that tiny arrow. We zoom in. There it is. Really small. That's the like activation energy there. Okay. And you have to draw in the activation energy for each separate step. Okay. Even though this first activation energy goes above and beyond the second one, you still have to draw in the second one because you've had this intermediate, you've had this sort of spot where things settle, right? But then they need a bit more energy. They need energy again to activate and react again.
So like while this overall reaction is thermodynamically favored because it's exothermic overall, kinetically it's different because our intermediates are closer, or like the first transition state is closer to the intermediates rather than the reactants. I don't know if that makes sense.
Yeah, so yeah, I mean, well, that's an important point, which is that there's this distinction between something being exothermic, right? Normally when we think about something being exothermic, like that's favorable, like that's a good thing, right?
Mm-hmm.
But then again, like, you know, lighting a fire is really exothermic, but it takes a lot of energy to do it, right? Your house doesn't spontaneously combust, so you know there's that activation energy right there, right? That is like a kind of kinetic thing that you have to deal with. Yeah, the idea of it being selective or not is still not really a kinetic thing, or well, it's kind of hard to say. So if we were to draw something that wasn't selective, right? So let's draw a halogenation that's not selective.
Mm-hmm.
Well, okay, it's going to need some activation energy to go up, right? But remember, by the Hammond postulate, we're saying what we start with has to be closer to the transition state than what we're ending with here, this intermediate, right? I'm going to write the same stuff as before. Maybe I'll be more specific and just say chlorine this time because we know what it really is. Then here we go to HCl, and then this R radical. Okay. And then we go down again. All right. Because, well, let's see, what do we get at the end? We got chlorine on this group, then we get this guy. Okay. The reason that like I knew how to draw this is because so we know it's overall exothermic.
Mm-hmm.
Right? Otherwise, you'd have to really put in a lot of energy and work to do it. But, well, this happens, right? This happens pretty easily in the lab. Just put chlorine gas on something and it'll chew right through. It's okay. We know it's exothermic, right? And we also know that intermediate energy is less than the starting energy or the reactant energy. right?
Mhm.
This comes from the Hammond postulate. Because, well, we said that this was a non-selective reaction, okay? So it doesn't care where it's going. It just cares about what you start with, right? So that means that what you start with has to be closer to the transition state. So, all right, that means we know that we go down. We know that we go down in, you know, this first part, right? And that comes from part 2 over here, right? And you also know that overall the whole thing has to go down, right? And that comes from part 1. So that means it has to start up high and then it goes down 1, then it has to go down again.
Right.
Yeah. I guess there's like a possibility. I don't think this could really happen, but maybe there's a possibility that it can like do this and then it goes like here, right? Which is still lower than the start, but maybe it went up from that intermediate. I don't really think that would happen though. Yeah. Okay.
So I guess that like these reasons would make a more significant deal, for instance, with like iodination, because kinetically, like it's not favored and thermodynamically it's not.
Yeah. Yeah, they would. So that's kind of why I mentioned earlier. I guess it's, yeah. So I think that was what it was, and I wasn't remembering it. But so the iodinization of something, so sticking an iodine on, is endothermic. That's why it's like not really so commonly used.
Mhm.
Yeah. So that would probably be a situation, and maybe just to really. So this iodination. I hope that's how you say it. So what it does is it starts from up here, from somewhere, wherever, right? And then it's selective. Right? But then once you're there, it goes way up because it's endothermic. Yeah. So I think that would be the case. That would be what happens. Yeah. It's worth double checking me on this because I have the feeling like the book or the lectures talk about this, and want to make sure I'm
Wait,
not.
you said it was down because it was selective, or is it supposed to?
Whoops. You're very much right. Yeah, sorry about that. I was following the other diagram. Yeah.
Oh, okay, cool. Thank you.
Yeah, I had that wrong. Okay, so it would actually be up. You're right. Well, then we're not sure what happens at the end, right? We just know at the start it goes up.
Yeah, it's just really slow and selective, and then endothermic on top of that.
Yeah, yeah. So it might either go up here or down to here, you know, as long as it's endothermic, right? Right, and then, you know, as long as it's endothermic. I'm writing off the page. Okay. Yeah, as long as it's endothermic, then that's kind of the point. And that makes it hard to do iodination. Yeah.
Thank you.
Cool. Let me look at another thing. this problem, which is, there it is. Okay, here we go. How much space do I have? A lot of space. Okay, cool. Right. So we're looking at 2-methylpropane, and well, you're not expected to know how to name things in the class, so why don't I just tell you what that is? So 2-methylpropane is propane, and then all right, it's got a methyl on the 2 position. Okay, that's not too crazy, right? Let's see, free radical chlorinization. Chlorination. Okay, what happens? Here we go. Chlorine, light. Well, we have primary, and primary, right? And I hope it's no surprise if I tell you that, well, there's a tertiary carbon here, and that's going to be, well, oh no, well, this is chlorination, right? I was about to go on and, you know, talk about this. So this chlorination will happen pretty, you know, non-selectively, right? Chlorine just goes after whatever hydrogens it has. Okay, well, there's 1 hydrogen over here on this tertiary carbon, and then let's look everywhere else and fill in. And oh my God, I'm gonna be here for ages. There's 9 other hydrogens. Okay. What's gonna be the major product?
The major product would be the chlorine substituted in for the tertiary hydrogen, but since chlorine is really reactive, it could be on the primary as well. And that's why you have those product ratios.
Yeah. So the idea is, at least what this problem is trying to get at, is that in terms of like what you would normally predict if you were given this, you might say, okay, well, look at that, right? It'll stick right onto there. It's a tertiary carbon, it's better, right? Yeah, chlorine doesn't care that much, but like it's still, I think it still shows a little bit of preference, like slightly. Okay, well, we would think it would go over there, right? But it's not that selective. It'll go on any of these hydrogens pretty closely, right? In fact, this following second part of the problem says it has this relative reactivities with each of these hydrogens, right?
Wait, I have a question about that actually.
Yeah.
So like I know that chlorine is like highly reactive and it doesn't really like have a typical preference in terms of like the carbons that it's attached to, but there's like this recitation problem in Ravalli's sheet where like it's a chlorination process, but then the chlorine comes in this cyclohexane, and there's like a double bond in the cyclohexane, and the chlorine only attaches to like 2 positions in comparison to like with this compound where it could actually attach to like the 1s and the tertiary. Do you know why? Like, is there something to do with like allelics that makes it prefer to like only attach to a select amount of locations?
Yeah.
Actually, I'm gonna just show it to you.
Okay. Let's see. Oh, okay. So in this case, in this problem, well, here we go. Let me just draw a little box to the side. So this problem is saying, I see what your problem. Yeah. So I see it's like this, and then there's chlorine, and there's this light, right?
Mm-hmm.
So that means, okay, we have this chlorine radical, and it's going to stick on somewhere,
Mm-hmm.
right? And well, one of the things that like hasn't really been mentioned about free radical halogenation so much is that it only works when your things have like single bonds, right? We don't, I don't think I've seen any situations where it happens where you have a double bond and you do free radical reaction on that double bond. Mm-hmm. So that is to say, these two over here,
mm-hmm.
these are off limits. Okay.
Are you saying there has to be like another, like just another hydrogen for it to replace? Like if there's only one hydrogen, then it typically wouldn't take the position of it?
Well, no. So you can do a reaction when there's just one hydrogen, right? I mean, here's a case, right? In fact, tertiary carbons are a lot better for this. Mm-hmm. They'll react a lot nicer because their radicals are more stable. It actually has more to do with this double bond, because the double bond affects like the energy of the radical. It makes it really unfavorable to have a radical there, like super unfavorable. It gets into like complicated reasons, which is kind of my like response to a lot of this sort of stuff. Mm-hmm. In general, when there's a double bond, I think there's I was actually looking through. Oh, there was like an exam problem like ages ago, where they actually asked something like this, where they gave you like, they give you benzene, right, which looks like this, and it's got hydrogens all over the place. But if you put it with chlorine and light, it's not gonna react. This is something you'll see again way down the line, and like that's also another thing that I've just been saying a lot, right? But this is like one of those things where you can't do any reactions with benzene, and in this case, it's not only because it's aromatic; it's also just because it has double bonds, and you can't do this reaction on double bonds. Mm-hmm. You will see in like 2 weeks that like that's not quite true, and there's something really fishy going on with what I'm talking about here. But for free radical halogenation, you can't attach to the double bonds.
Oh yeah, like I get it in terms of like the ring itself, but can you explain, like say for instance we have like a R group attached to that benzylic ring, why that, let's say for instance we were doing a bromination and we had to like compare like, okay, we have some tertiary carbons in like one compound, but then we have this other compound with the benzylic ring attached to it. They say that the benzylic ring compound is like more stable for that bromine or chlorine to like attach to. Can you explain why? Does it have to do, I don't know, does it have to do something with like either resonance or just like the way that the bonds are set up with electronegativity?
So in that case, so whenever you have a benzylic or allylic, it's because of resonance.
Gotcha.
It is because that radical can move around. The problem that you showed with those solutions. So what they actually had was, so they had one chlorine here, and then they had the other chlorine over here opposite to it. Mm-hmm. And I mean, the reason that they did that is because it can go on any of these hydrogens, mm-hmm. right? And you'll notice that like these two and these two, they're the same thing. Because you could just flip the molecule around.
Yeah.
Right? So what they've really drawn here in the answer is any of the possible hydrogens. Like that chlorine has attacked any of the possible hydrogens there.
Gotcha. Yeah. All right. Thank you.
Yeah. And just to emphasize the point, if this was bromine, if this was bromination, and I'm gonna write something called NBS here. Have you seen NBS? No. Okay.
Yeah, Professor Molander talked about it in his lecture.
Okay, yeah.
Yeah.
So the reason that we use NBS is not yet clear to you, or maybe it is, but well, maybe he mentioned it, but you'll see in like, well, pretty soon in the class, like in 2 weeks or so, why we use NBS instead of just Br2 bromine. But you could just take my word on this. NBS here works, and it adds a bromine. That's what the B stands for, right? So you could use NBS and light instead, and this one will be selective, okay? And it will only go on the allylic position. It'll also go on this other carbon too, but we could just flip the molecule around. It's the same thing. Okay. Yeah. Here we go. Okay, so if we're going up here, back to chlorine, which is not selective, right? And then, okay, well, primary hydrogens react with, let's say, 1 unit of reactivity. I don't know. They're relative, so it's fine, right? And then tertiary carbons react with 5, right? Well, there's 9 primary carbons, and there's 1 tertiary carbon, right? And then, oh, well, I don't need to write multiplying because I already did, right? So this gives 9 relative reactivity, and this one over here gives 5 relative reactivity, right? So if we have this as a ratio, so 9 out of 14 times, out of 9 plus 5 times, right, we will get this right here, and then 5 out of those 14 times, we'll get this other one, the one on the tertiary, right? Which is, well, that's kind of opposite to what we would have expected, because tertiary is nicer, right? It's better to have it on the tertiary carbon, but well, there's so many of those primary hydrogens that it kind of outdoes that, right? There's just more of it. This is kind of just to say, like, these reactions can be kind of like messy. You can get a lot of stuff depending on how many hydrogens of each kind you have. You might get different stuff. Also, just besides the fact that a lot of different things can happen at the end with, you know, termination and all that. But well, I guess this doesn't go into it that much, but yeah. Here we go. C, free radical bromination of 2-methylpropane. It's much more selective. Explain the selectivity difference. Use Hammond postulate. Okay. Well, I think we've kind of beaten this one to death, right? The Hammond postulate, so it's just the fact that this is the most stable intermediate. Right? And in the case of in the case of bromine, we're going from, oops, yeah, that's not the compound. Right? Okay, right. So the transition state is closer to the intermediate, right? So you're just going to get the intermediate that's more stable, so you're just going to get the selective tertiary bromination. Okay. Last one. Why not fluorination, iodination? That's the word for it, as it turns out. It's iodination, as opposed to whatever garbled nonsense I've been saying all along.
What's the last thing you said for the last one? You just said that the transition state is closer to the intermediate, right?
Yeah.
Okay.
Yep. Okay. So why not iodination and fluorination? So So iodination, this is endothermic. It's endothermic, and it's like hard to do, right? It's hard to get it to work. Iodine in general, this is something that you'll see again, like, I say this so much, way down the line. Iodine, it usually, if you want to do something with iodine, it might take, if you want to attach an iodine, it's kind of hard. Even though iodine's really nice, you'll see that it's like the ideal leaving group. Like, there's such a nice leaving group. It comes off like butter, right? But putting it on is a little bit more tough. Okay. So getting an iodine on is a little bit more challenging, right? And then fluorination. Anybody know why you can't do fluorination?
Is it because the bond strength is too high? Like the light doesn't break it in the first place? Or is it because it goes out of control in the reaction?
Yeah, I think it's more the latter. I actually don't even think you need light to break the fluorine-fluorine bond. Like fluorine. So, well, I'm not certain because like people don't really try to do this very much. At least as far as I'm aware, it's like not a commonly tried reaction just because it'll get so messy. But yeah, I think fluorine on its own is reactive enough that it just won't stop at anything, and it'll kind of just burn through whatever you're using. Like in some cases, literally, like it'll just get it on fire because it's so hard to control. So fluorination is just, I don't know, too exothermic, right? It's not going to be selective at all. In fact, it's just going to like destroy whatever you have, probably. So we don't really use it that much. Okay. Let me go over here. Okay. And then, let's see. We're just about out of time. Save 2. There we go. Yeah, there's one last problem on the worksheet, and I mean I'll just go through the first part of it. The second part is to draw a full mechanism for free radical bromination. For that one, I will tell you, review that and look in the book and look at the past lecture. It is the same mechanism as always. It's kind of like one of those cookie cutter or cut and paste or whatever cut related analogy you want to make to it. It's just one of those things where like you sort of write the same thing each time. It's just connected to a different thing, right? So we'll just stick with the first 2 parts. So the first part is, okay, write the free radical bromination of propylbenzene. That's propylbenzene, okay? So what do we have? Well, we have a hydrogen here on this tertiary benzylic carbon, and oh man, we really can't get better than that, right? And then we have these 2 primary carbons. We're not going to use those, right? Okay. So it's going to attach to the most substituted place. Not only the most substituted place, but also the benzylic place, which is where it gets its resonance, where it gets its stability. Okay. And well, it just says predict the product. At this point, if they say predict the product, you don't need to draw out the mechanism, right? You know what the product is. The bromine there. That's it. Okay. Next compound is decolin, which we've gotten a lot of experience with. Okay. And well, we can look at what we have here, and there's a lot of secondary hydrogens, but well, there's also these two guys over here, right? So here we go, bromine. These are both tertiary carbons, and I'm not considering whether it's cis or transdecolin or any stereochemistry or anything, right? But it just turns into a bromine on one of these, the tertiary carbons. Right? That's it.
Could you get bromines on both, or would that not happen?
Usually we're just gonna assume that one bromine goes on, and just one. You could get multiple. So I'm trying to think. I think in fact that so when we think about the radical stability, right? Things that donate electrons into that radical make it more stable, right? But bromine is electronegative, so it pulls electrons away. So that radical that would happen on this thing would actually be less stable. So it's kind of less likely that would happen, right? That first bromination is the easiest, but after that, you'll have to remember the inductive effect from before, right? Everybody's absolute favorite thing, which nobody ever teaches you, but you just expect it to know. So you get this effect from the inductive effect where the bromine is pulling electrons away. And so it's slightly less favorable. It's pretty minor, right? And the kind of real answer is we're just gonna say that it only attaches once. But there's some slight justification for it. Yeah. Also, what people would kind of actually do, or what might be like more common to do, is actually just to use NBS, right? And the nice thing about NBS is that it only has one bromine. It's just one bromine, right? So you can put in exactly one equivalent of NBS and you know what it's gonna do, right? Or at least maybe it won't react all the way, but well, you have to kind of purify these things anyway. You have to kind of like, yeah, you have to do something to clean the stuff out. So yeah, you could do this too. Okay, and then the last one is, oh Jesus, cyclopentene, which looks like this. Okay, 1,2-dimethylcyclopentene. I think it's this one. I don't know. Okay, well you can look it up, but what the structure of it is, right? But we look for whatever position is allylic because that's what NBS does. Allylic bromination, we always use NBS. Okay, well there's one, there's another. Okay, so we wind up getting a whole bunch of products. So there's one that's really nice, plus there's one, plus there's another. Okay. Oh, oops. That wasn't the structure of that compound. I tried to go from the name to the actual structure by my own naming skills, which are kind of weak, right? This is not the structure in the compound, but whatever. Hey, it was good practice anyway. The actual structure in the compound was this, but I think you'll see that it's quite similar, right? So this thing gives you there, or let me make this a little bit quicker. There's one, you could get one there, or you can get one there. Okay, that's it. Okay. That gets through all of it. That kind of covers what we had to talk about. Most of the problems I know were free radical questions. You will see more about stereochemistry in the lectures. And I think the biggest thing is that R and S rule, because there will be some problem that asks you to designate whether things are R or S. Someone will ask you. So yeah. Okay. Let me mention one last thing. It came to mind, and this has come up before on the exams, and hopefully I might save you from losing like a bunch of points. And I know this is like the last thing to say, and I meant to say it earlier. And it's totally unrelated to everything else. It's just, I know it's come up before, so it's worth knowing. Nitrogens can be chiral centers as well, because, well, they have electrons, which take up an orbital, right? So if we have something that looks like this is a chiral center as well, okay? Okay, it is. This is just worth knowing. It is one of these. The only thing is that nitrogens can flip. These electrons can go up or down, right? This whole thing can flip like an umbrella in or out, okay? So it's a chiral center, but it can flip easily. It can flip easily. Okay, that's the only thing, right? So that's why we usually don't draw it as being wedges or dashes, right? Because, well, it doesn't matter what we draw it as, it's just going to turn around anyway. Okay. Sorry, I forgot about that earlier. I just wanted to get that one last thing in, because I don't know, maybe it'll come up and maybe it'll be important and useful. It's kind of a trick thing that occasionally shows up. Okay. Okay. I've talked for longer than I should be talking. If you haven't filled out the sign-in form, I just sent the link to that in the chat. Please fill that out. It's quick, it's short, it's simple. Okay. Good luck on that quiz later in the week. How about I stop sharing my screen? Okay. Good luck on that quiz later this week. You will do fantastic. You are ready. You know all of the material already before it even happened in the lecture. Okay. Good luck. You will do well. I have full confidence in everyone.